part where I discuss the question of what additional length scales we may have in the problem, right? So the case of a bounded domain, and now there is another possible situation, inclusion or more traditionally an obstacle in an otherwise free space. Okay, so what I mean is that you can have an obstacle, right? So waves propagate outside. Or you have an inclusion, so this perforation in the middle of this obstacle is actually filled with some material, and waves propagate through it. So this is more traditional in questions of scattering. This is something that actually has been looked at. This kind of problem has a very, very recent history. So only recently people have started looking at such transmission problems. So there are very few works, like by Schechter. Schechter, for example, started some questions about transmission problems, but certainly not in the context of wave propagation and scattering. Actually, part of Yuan's work currently is on this sort of setup. So here we have a length scale which we label by L, right? Lowercase L. So same here. You can pick any. You can measure it in any. So we assume that the obstacle is more or less of the same of comparable sizes, no matter which direction you will from which direction you look at it. And here we will have the wavelength lambda. Oh, here we will have the wavelength lambda that corresponds to the waves for the waves that propagate outside. And here we will have two wavelengths, right? So there are actually more length scale parameters here in this problem. This is wavelength, say lambda 1, and here I have wavelength lambda 2. Okay, so and I leave this as a kind of exercise. Yeah. Yes, sure. Yeah. So the frequency is fixed. So. The reason I'm asking, yeah. To specify exactly the there's a sort of very relaxed. Well, but how can you not fix a frequency for waves propagating through a medium like this?
Oh, like Daniela?
No, but they didn't have different frequencies here and here.
Yeah, but
it was all omega. It was all omega throughout. So okay, so exercise 1. This is the first actual written exercise I suggest. Is non-dimensionalize this. Non-dimensionalized wave equation. Okay, so I use capital U plus some boundary conditions. One of those, you can take one of those or a mixture of those that I mentioned for the bounded domain. Of course, in the case of the transmission problem, you will have some sort of transmission boundary conditions, but I will not go into that right now. So, and the questions here are, well, I already said what the wavelengths are involved here, and well, an easy question: how many dimensionless parameters are there?
That's a carbon.
And another question is, by analogy with the case of bounded domain, are long wave / short wave approximations mean? Okay, so something to think about. And I'll quickly move on from this, so to the case, to a situation C, where we will edge closer to what Stephen has been talking about. So the case of what one may think, what one may call as a highly heterogeneous medium. Of course, in general, you can have as many length scales as you like if you put inclusions of different sizes, but we will be assuming that all of these guys, they have more or less the same, well, comparable sizes in relation to each other, right? So this sort of medium has been touched upon in some approaches. It's just say that you can actually study a rather general problem like this, and one of them is called G convergence, for example. So Igor here is an expert on non-periodic heterogeneous media. So we will focus, however, on the periodic case. So when these inclusions have the same shape. Yeah, so here you can also, so the stochastic approach is also quite relevant here. So maybe stochastic homogenization. But I haven't said what homogenization is yet, so I'll put it in quotes. Stochastic homogenization. So we will focus on a particular setting. A periodic case of periodic. So what it means is that all these guys, which I will be henceforth assuming to be inclusions, but they could be perforations. But I'll assume them to be inclusions, and they are of the same shape and size, distributed periodically. Right. So this is where eventually we will apply the block-defined approach first, and then use that as a basis for our analysis. So here you might think of a two-dimensional medium. So what does two-dimensional medium mean? Well, this could be the result of studying a three-dimensional medium where the inclusions have the shape of fibers. Or you can look at a three-dimensional medium which is not reducible to 2D, where you have these three-dimensional inclusions. Right? So, and its periodicity cells, they are in 3D obviously. So you can imagine. So that it's also periodically continued in the third direction, away from us. Okay, so here I have the same kind of equation, but now I put mu in between the gradients Stephen did from the outset. And the meaning of rho and mu is still the same. So the derivation is the same as for the classical wave equation. Essentially, this is, I haven't said this, but I will now. So this is, this equation is obtained from the idea of by balancing the momentum, right, on an arbitrary sub-region of this medium. Okay, so essentially it's a second Newton's law applied to that. And mu here is going to be assumed is periodic, but periodic with period d, which is a dimensional quantity. So it's measured in meters or whatever dimensions of units of length. So I will think of mu as being some function mu tilde of x over d, where mu tilde is one periodic. So it's actually periodic with the period, right? With the period that is obtained from a single cell by scaling. So, but what I mean by one periodic is that this cell has size 1 in all directions. So that's what I mean by one periodic. So one periodic, or actually we will use this symbol as well. So just to indicate that this is a cell in 2 or 3D. So what this means is that mu tilde of x of y, I will use y, following Stephen's suggestion, yj plus ej equals mu tilde of yj for all j and yj. Okay, I'm not discussing at the moment some analytical more precise analytical assumptions about this function.
What does yj? Why?
Oh, why? Yeah. Thank you. Yeah. Why? Okay. Okay. So I'm not discussing sort of more precise analytical assumptions on this function. So let's just assume that that it is piecewise smooth, right? So it could be piecewise continuous. You can even think of it as being, piecewise constant. You can think of it as piecewise constant. So in other words, it takes one value here and another value here. In fact, this is what we will be mostly looking at in the pretty much the rest of my course. Okay, so as a result, we have x over d here with mu tilde, and I will try to look for time harmonic waves, which are a generalization of those plane waves that I looked at to start with in the case of a homogeneous medium. And here, W of x is to be determined, right? So plane waves exactly are not available, but some analogs of plane waves will be, like Stephen mentioned on a couple of occasions. So this is where the link with what Stephen was talking about gets stronger and stronger. Okay, so we substitute this into the equation, and we get minus rho omega squared W of x minus divergence, and I'll be working within this piecewise constant case. So what I mean is that it's this function that takes one of two values, and it's periodic with period d. Sorry, the function is periodic with period 1, but then For the actual medium, it has period D. And then I have e to the I omega t, which I can cancel out. So it's similar to what we were doing for the case of a bounded domain. It was exactly the same kind of calculation, it's just that the coefficient was constant. So I cancel this out, and I end up with the equation, basically just like I can much erase it here. Okay, so here we have a two-component medium. So there are two wavelengths. I already mentioned that in the case of a single inclusion. So now we have omega squared is time frequency, and it's omega is 2 pi c1 over lambda 1 equals 2 pi c2 over lambda 2. These are the wave speeds in homogeneous media in basically whole spaces filled with the medium 1 or medium 2. And these are the corresponding wavelengths. Okay, so now I'm gonna non-dimensionalize here. And for non-dimensionalization, there are actually different strategies. I could pick, for example, lambda 1 or lambda 2 as a length scale parameter. But and I will leave that. I won't actually do it here. I will leave that as an exercise. But since I want to deal with, since I want to make a link to homogenization, and I want to talk about what I call what is called wave packets eventually. So I will actually introduce. I will think about just some kind of reference length scale here. This is done for the reason of the construction for the needs of the construction of a wave packet. Right? We will see it in a few minutes. Okay, so what I will do now is I will think of some reference length scale, which could be either lambda 1 or lambda 2 if you wish, but it doesn't have to be. So it could be, for example, also the wavelength for a given frequency omega, the wavelength of waves propagating in a third medium, right? Like some kind of some other third reference medium, right? So, and I will refer to this as capital L. So then I will make the kind of rescaling that I will do the kind of rescaling that I did for the case of a bounded domain. Okay, so I want to keep this here. And I will see what happens, right? So W of x tilde is capital W of x tilde L. This is what is W of x, right? Okay. So, and I'm going to write down the equation for this. This will be a dimensionless equation. Of course, for it to be completely dimensionless, I will still have to scale W, but since it's a linear problem, I don't do that. I don't care. Right? So this gives me, in the same way as before, for the bounded domain, it gives me minus rho omega squared W minus mu2 1 over L squared, the gradient with respect to x tilde, mu1 over mu2, 1, x tilde over epsilon, grad x tilde w equals 0. So epsilon here is the ratio of t, the period, and this reference length here. So now dividing through by rho omega squared, I end up with what looks like an eigenvalue equation. But of course, I have not set any boundary conditions yet. In fact, I'm looking at the whole space still. So just let's look at this as an equation rather than as a problem. So this is mu1 over mu2, 1, x tilde over epsilon, grad x tilde w equals 0, so equals rho over mu2 omega squared L squared w. And this is what I would like to label by z, and I want to indicate that it's a function of omega. Yeah. In fact, to make it a genuine function of omega is the reason why I chose a reference length scale. If I chose, and that's going to be an exercise, if I chose capital L, yes. So if I chose L1, thank you. If I chose L1, L to be lambda 1 or lambda 2, then I would get 1 here. You can check that directly. So, but I won't have an arbitrary spectral parameter. I want to have still a function of omega. If L was lambda 2, that would be 1. This is exactly 1. That's number 1. If I divide it through by mu1, the other way around, and chose L to be capital L to be lambda 1, the same. Let's solve. But I want to construct wave packets. So I want this to be a function of omega. I don't want it to be 1. That's why I need L. So actually, this is a point that we have to kind of accept here, that if we want to start talking about functions, about waves that actually have finite energy, that are wave packets. What's a wave packet? A wave packet is a kind of wave that looks something like this, right? So a wave like this is what we want to see in reality to give us finite energy, right? So this is what a finite energy solution looks like. And in order to end up, so the wave packet has a length scale. A typical length scale kind of implied by the very fact of the existence of this wave packet. So that's why I actually need to bring in an additional reference length scale.
Because we are sitting in the situation of highly dispersed ideas, so your wave packets will disperse from that by part. Okay. Yeah, but then
No, just think about some L. Let's not. I'm just saying why L is necessary. I'm not saying what L is. Right?
If you're trying to,
so,
you spend some power the way L.
Okay.
There is no such thing. T equals minus. I'm not sure about that.
So
if it's a finite zero, that's the problem.
okay, so I'll write it here: z of omega equals rho over mu2 omega squared and squared, and I will replace this by z. let's write it in a different way. So we have period epsilon here. So what does it mean? Well, maybe it's not a good way of formulating the question. So let's just think a little bit about this and sort of reformulate and think about it maybe in some kind of more mathematical way, in terms of what one would call an operator. So this is where the word operator comes in, right? So what I want to do is I want to rescale to period 1 again. Well, I haven't done it yet, so it's just rescaling to period 1. So that is the period, right, that we had. So I'm going to write x hat equals x tilde over epsilon, and so w hat of x hat is w tilde of epsilon x hat, and I want to write the problem on w hat. Right, so it's quite straightforward, right? I just get in the same way I got 1 over L squared outside when I was non-dimensionalizing. I'm going to get 1 over epsilon squared out of here, and this will give me just this. So gradient of x hat. So this function is periodic with this period now. And this is genuinely the kind of function that Stephen has been talking about. So period, there is no small parameter there. He did mention that the period may get smaller, so then you should think about this problem. So the period here is epsilon, and we can make epsilon become smaller and smaller. So, but I would like to now make a link to homogenization and operator theory simultaneously by looking at this problem, and I'm gonna at this equation, and I'm gonna refer to the expression on the left as an operator A, whatever that means, right? So basically, you can think of it as the action of this differential expression. So taking the gradient, multiplying it by that function, taking the divergence and multiplying, and that's it, right? So I want to refer to this as a omega hat, maybe even without this minus, just like that. Okay, and I want to ask myself. So, but you can think simultaneously about this formulation where we have period epsilon. Because the link between them is obviously very straightforward, just a scaling. So I want to ask myself whether I may not pass from this formulation to what I would like to call a homogenized formulation, or homogenized equation that will be an equation of a similar structure, but with this function replaced by a constant one. So I want to end up with something like this by some sort of process where A always constant. And of course, the solutions have to be labeled by a different, yet another letter. So I'll attach the label onto it. And the corresponding sort of differential operator is labeled by A comp. Okay, so this process, well, and sort of more details of it should be fleshed out in what's coming, is what I refer to as homogenization. But in what sense do I mean this? I pass to 0 here. So the sense in which I will mean this is that for f in L2, one has 1 over epsilon A plus Z identity inverse converges to 1 over epsilon squared. 1 over epsilon squared A 4 plus identity inverse. Yeah. Okay, so this is the sense in which I will understand the passage from here to here. This is a rigorous mathematical expression of this informal replacement. We will see towards the end of this lecture how this process has been carried out in the past, but I want to take you right to where the sort of the state of the art from my perspective is right now. So, and I want to bring in the notion of an operator. That's why I'm giving this definition. Okay, so and why are we interested in this kind of convergence? Because ultimately we're interested in the wave propagation for wave packets, with finite energy. Yes, that's sure. I don't want to make things too heavy, too complicated. We can be more specific about that later. So in particular, we are interested in this kind of convergence as well. So why are we interested in this? Okay, so we're interested because we want to see into, we want to quantify propagation of wave packets. What are wave packets? Wave packets are okay, so I had W, right, that solved this equation. So I'll also sort of indicate here that W is actually it depends on epsilon, and it's a function of x tilde, obviously, and also it depends on this parameter Z, which remember was a function of omega. And so by wave packet, I mean this kind of drawing. So this is x tilde over epsilon. It's the same thing as x over L, where L was that reference length scale Z of omega e to the I omega t phi of omega d omega, where phi is a function with well, let's say continuous function with compact support. Okay, so these are the guys, these are the true waves that I'm interested in. This function omega, well, it's a nice starting point for a wave, but it doesn't have finite energy. It's a generalization of that exponent that we talked about at the beginning for the homogeneous medium. But eventually I want to quantify things, right? So this is the keyword here. And in order to be able to quantify, I need to start talking about wave packets. So, and wave packets are actually waves with finite energy, like this. They are Fourier transforms in omega of these building blocks, these functions omega epsilon that I get from here. With multiplied by a nice modified by, well, it's not modification, so multiplied by a function of omega with compact support. So, and this kind of convergence appropriately enhanced guarantees the convergence of wave packets. So, yes.
Now you say something error or something.
Oh, sorry. Yeah.
Normally, think of the right.
Yeah. Sorry. This
Do you want to go epsilon?
I want the difference. Yeah, I want this to behave like. Sorry, shouldn't have used the right error. So no, yes. Yeah. Thanks. Yeah. So what this still remains is basically the difference. The difference between these two is actually small, right? So it goes to 0 and epsilon goes to 0. Yeah. So it's an asymptotics rather than a linear. Okay.
I mean, how do you grow? Yeah, I mean, you really want to sense that it's not bad. It's not really far away, but it's still one of the reasons where
No.
You don't want to do that. Oh, that's what this is like. It's that finite. I mean, doesn't it just go away? Because I mean, if you fix that, the normal second meaning is that for the rest of the
No, it's fine. It's fine.
So you should have the scale so that's a what
Yeah. Something is right.
Before you start writing everything was fine because you could cancel out the scaling part of the function itself, both the right and the left. But once you pass over to the formulation on the right hand side, this is now the problem. So you must rescale those things.
Yes.
I was waiting for that actually to happen.
Okay.
Because I made this particular mistake like a hundred times. So you're multiplying it by
Let's leave this like this, right? Because we're gonna go. Yeah, it's fine.
It's easily fixable. You have to multiply that by the same silence degree.
What?
You have to multiply that by something as well. By itself.
Yeah.
And another is right. You should have done that by the scaling. You were scaling.
Let's just leave this for now. We'll come back to this. Okay. So
you think that's right? No, it's not.
No, it's not right. But I want to explain why. I want to make a link between two eigenvalue equations, right? Yeah.
So is that really what you mean?
No. Let's get back to that later. Okay. Okay. Just yeah. Okay, so
No, this says it doesn't.
okay, so we don't have time. We need to move on. I have only 15 minutes left. So.
I understand that.
Yeah.
But basically saying that the solution to the homogeneous equation converges in some sense or closely in some sort of.
Well, that's what I wrote initially. Yes.
Yes, and you shouldn't have written the results at all.
That's
no results, just the solutions to the homogeneous equations. No F's, no right hand side. Just
what solutions to
you put
this function in what sense converge?
in some sense.
Well, you'll do it when you give your talk. So okay. Yeah. So let's just understand it in this sense, in some kind of it. Well, I mean the detail will get fleshed out later. We want to approximate solutions to the problem with the right hand side, F solutions to the problem, to the epsilon dependent problem by the solution to the homogenized problem. So I should have never written the norm of the difference converges to zero. So I should have left it where it was. But I initially used the arrow incorrect. So the asymptotics in some sense, the asymptotics of this solution is given by this expression. Okay, so yes.
And one. In the super.
Yes. So just to mention, sort of give quick run through mathematical methods for homogenization. Okay, so here we have stationary approaches, what one can refer to as stationary approaches. And non-stationary, right? Naturally. So this is where the realm in which waves live. So for the description of waves. So here we have the Murat-Tatar energy method. This is sometimes referred to as compensated compartments. G convergence, two-scale convergence, and so also for nonlinear problems, gamma convergence. Here in this column, I have H measures, or more generally microlocal defect measures. And also operator norm estimates. This is the kind of estimate where we will be looking at the difference that we were just that we have this heated argument about. So So both of them, both of these columns, when they will produce this object, they call this matrix of constant coefficients. And I will quickly run through this method to show how this constant matrix is obtained by a rather straightforward argument. Okay, and then we'll move on to the more advanced sort of operator estimates. Okay, so for the stationary problems and for the Murat-Tatar energy method in particular, we look at the bounded domain omega. So this is now non-dimensional. Right, so this is the kind of arrangement formulation that Yuan mentioned in his lectures, right? And by what is called a compactness argument, we can show that. So I'll leave this guy here. Typically, it's not written when the Murat-Tatar method is presented, but I want to make a link to the operating of estimates, so I will leave it.
Where is it?
Oh, Z, okay. Thanks. Okay, so and we'll assume here that Z is just a positive, real positive number. Okay, so
I want the spectrum.
no, it's not on the spectrum.
Ah, it's plus.
Okay, so in the strong form, this okay, so I don't need to say this. This is pretty clear from what I've said up to this point. So this is a rational formulation for the kind of problem that was represented by this minus one over epsilon a epsilon 1 over epsilon squared a epsilon plus z inverse. Okay, so one can show that a sequence of solutions, so this is a sequence parameterized by epsilon, that it is bounded in H1 on omega. And so I can extract a weakly convergent subsequence, convergent weakly in H1 that is up to subsequent strongly in O2. So this gives me convergence. Oh, yeah, I'm considering the Dirichlet problem. So I'm looking for functions u epsilon that are in the space H10, let's say. Right? So weakly converges to the form after subsequence, right? So, and here we pass to making several observations that are crucial for this Murat-Tatar method. Observation number one is that the minus divergence of A of x over epsilon grad epsilon is f minus u epsilon, and this strongly converges in O2 to f minus u co up to subsequence. Second, so this guy is divergent free, solenoidal. Its divergence is not zero, but it converges in O2 to some fixed function. Okay. Now this guy. Okay, so I need at this point I need to introduce solutions, introduce functions and sign, we'll call them sign, such that the divergence of minus divergence of A of Y grad and psi plus psi is 0 for any fixed psi in RD. Okay, so these are the so-called unit cell solutions. And because they satisfy this equation, okay, and because and clearly, gradient of m psi plus psi is curl-free. So we have a function that is not divergent-free, but the divergence converges to a fixed function, and then a function which is curl-free. On the other hand, so I'm working with this object here. So I'm going to be working with this object. So here I have said something about A of x over epsilon times grad u epsilon and about some auxiliary function. On the other hand, so observation 2, grad of u epsilon is curl-free. And when I pull A of y onto this object, the divergence of A times the gradient of m psi plus psi is 0. So these guys curl free and these guys divergent free. So this allows me these two observations allow me to look at this object in two different ways. Right, so I have to assume that the matrix A is symmetric, of course. This function A is actually takes values in symmetric matrices. So where phi, so we'll put phi psi, where phi psi is by definition epsilon n psi of x over epsilon plus psi dot x. F psi x. So the compensated compartments theorem says that when you have a function that is curl-free and a function whose divergence converges to a fixed function, then the inner product converges in some sense. It's not important in what sense. It's actually weak star in L1. It converges to the product of the weak L2 limits of these functions. So the weak L2 limit of this is what I would like to call T home, the homogenized flux. So this is the lim again up to a subsequence of A of x over epsilon grad to epsilon. Okay, this guy, it's easy to work out. But this guy, I take the gradient, and then this is a rapidly oscillating periodic function. So we period epsilon, so it will converge to the mean of this function. So this converges to the mean. So the whole thing converges to the inner product of equal and the mean of this, which in turn is psi, because the mean of the gradient is 0. So this is the integral over the cell of grad and psi plus psi. On the other hand, I can write it in this way and apply the compensated compactness theorem here. So this guy is still free, this guy is divergence free, and so the inner product must converge weakly in L1, weak star in L1 to the product of their limits. Now the limit of this guy, is the gradient of the solution to the homogenized problem, Q4. And so the whole thing converges to the inner product, and the limit of this guy, since it's periodic in epsilon periodic, it will converge to the mean of A times grad n psi plus psi. So I have passed the limit in the same expression in two different ways, so the two limits coincide. This gives me exactly the formula for P home. So P home. So these two passages to the limit imply that P home dot psi equals grad Q home dot A grad and psi plus psi. And so from here immediately I have that P home is some constant matrix I hope times grad U home, where A home is this guy. Okay, so it's quick, but it's not, by far it's not ideal because it doesn't give us the kind of operator non-convergence, well, that's the convergence of operators that we were talking about. So I have to finish now, and next time I will continue with I will discuss. So eventually, so in the final lecture, we will talk about first of all, what approach one may take to prove the operator convergence, the one that guarantees the convergence of wave files. And secondly, what happens when this matrix, this function defined on the unit cell loses the condition of uniform ellipticity. So all this was okay under the assumption of uniform ellipticity of this function. Okay, so loss of uniform ellipticity will give us a completely different result to what we have obtained here. So maybe I should say that this relationship that we have established today, in particular, gives us the convergence of U epsilon to U home that solves this variational problem. U home. And this is, of course, the kind of equation that we're looking for, but we only have weak convergence in H1. This is weak convergence in H1 to the solution of the problem minus divergence of A home, grad U home plus Z U home equals F. So this result will fail to hold if we drop the assumption of uniform ellipticity on A. So this will be the conclusion of my lectures.